Welcome back to another training video using the UK electrical simulator. In this video, we're going to complete our discussion on wiring solar panels in different series and parallel arrangements. We'll compare the voltage and current levels for two setups and show how those values affect the choice of solar charge controller and battery bank. On the workspace, we have two solar panel arrays. Both arrays use 6 350-watt solar panels. Each panel has an open circuit voltage, or VOC, of around 41.5 volts, and a working voltage, or VMP, of around 34.5 volts when operating under load. The system on the left is wired as 3 strings of 2 panels in series, with those 3 strings then connected in parallel. This is often written as a 2S3P setup. This array is connected to an MPPT 150/70 charge controller and a 48-volt battery bank, whereas the system on the right is wired as 2 strings of 3 panels in series, with those 2 strings then connected in parallel, often written as a 3S2P. This second setup is connected with the same model of charge controller and battery bank. Before switching anything on, we can compare the open circuit voltage of each array. On the left-hand system, 2 panels in series gives us roughly 2 times 41.5 volts, which is about 83 volts. On the right-hand system, 3 panels in series gives us roughly 3 times 41.5 volts, which is about 124 volts. Both arrangements are below the 150 volt maximum PV input voltage of the selected charge controller, so both can be suitable from a voltage point of view. However, in a real installation, we would still need to allow for cold weather voltage rise and check the manufacturer's data before confirming the final design. Now, before we switch on the charge controllers, we'll enable the wire flow animation so we can see more clearly how each system is wired. We can do that by placing a tick in the wire flow animation option. Let's now switch on the first charge controller. We can clearly see current flowing from the solar panel array to the controller, and then from the controller to the battery bank. Each pair of panels in series contributes around 5 amps. Because there are 3 of these strings connected in parallel, the total current feeding the charge controller is roughly 15 amps. We can also see that the voltage has changed. The open circuit voltage was around 83 volts, but once the system is working under load, the voltage drops closer to the panel's working voltage. In this case, it drops to around 69 volts. That is because the panels are now operating nearer their VMP rather than their VOC. Now let's switch on the second charge controller. This time each string contains 3 panels in series. The current through a series string remains roughly the same, so each string still contributes around 5 amps. However, because there are only 2 parallel strings, the total current feeding the second charge controller is around 10 amps. Again, we can see the voltage drop under load. The open circuit voltage was around 124 volts, but once the panels are working, the voltage drops closer to around 103 volts. So the two systems behave differently on the PV input side. The left system has a lower voltage and a higher current, whereas the right system has a higher voltage and a lower current. But even though the PV input voltage and current are different, both systems are supplying the same total panel power, because both systems use the same number and rating of solar panels. This is an important point, as the job of the MPPT charge controller is to take the available power from the solar array and convert it into the correct charging voltage and current for the battery bank. So the controller may receive power at one voltage and current on the PV side, then deliver that power at a different voltage and current on the battery side. For example, the PV side may be operating at a higher voltage and lower current. The controller can then step that down to the correct battery charging voltage, while increasing the charging current. That is why the PV input current and battery charge current are not always the same. Let's now test the effect of sunlight on the overall system by moving the sun slider. When we reduce the sun level, the available panel current reduces, but when we increase the sun level, the available current increases. The voltage may remain broadly similar, but the current and available power will change with the amount of sunlight. This is why shading, panel angle, weather, and time of day all affect how much useful power the solar array can deliver. Now let's switch off both charge controllers to make some changes. We'll change the left-hand charge controller to a smaller MPPT 100/30 model. This controller can handle up to 100 volts PV inputs, so the left-hand array, at around 83 volts open circuit, is still within the voltage limit. It also has a lower maximum charge current, with a maximum battery charge output of 30 amps. However, as soon as we power on the controller, we get a battery bank fault warning. This is because this MPPT model in the simulator is designed for 12 volt or 24 volt batteries, and we still have a 48 volt battery connected. The voltage of the solar array is not the only thing we need to check. We also need to make sure the charge controller is suitable for the battery bank voltage. Let's quickly change the battery to a 24 volt model and try again. This time the charge controller starts operating correctly. It can now detect a suitable battery and begin charging. Because this controller has a maximum charge current of 30 amps, it will limit the charge current to that value, even if the solar array could produce more power. In other words, the controller rating can become the limiting factor. So when choosing a solar charge controller, we need to check several things. The maximum PV open circuit voltage must not be exceeded. The PV input current must be within the controller's rating. The battery bank voltage must be supported. The maximum charge current must be suitable for the battery bank. And the total panel power must be appropriate for the controller. This is why solar design is not just about adding more panels. The panels, controller, battery bank, cables, connectors, isolators, and protective devices all have to work together as one system. To summarize this demonstration, the 2S3P array gives us a lower voltage and higher current, whereas the 3S2P array gives us a higher voltage and lower current. Both can work with the MPPT 150/70 model, because both are within the controller's voltage range and suitable for the 48 volt battery bank. But the smaller MPPT 100/30 model is only suitable when the battery voltage and current limits match the controller's specification. I hope you've enjoyed this video looking at different solar panel series and parallel arrangements, and how they affect voltage, current, charge controller selection, and battery charging. In the next video, we'll spend some time looking at the different charging stages used by a solar charge controller when charging a battery. We'll explain what happens during bulk, absorption and float, and how the controller changes the voltage and current as the battery becomes more fully charged. Please like, subscribe, and leave a comment below.